All right, line A5, we're going to take a look at learning task 6. Once again, we're working at open circuits in three-phase. We are now going to start taking a look at open delta types of circuits. Once again, what we are looking at is we are looking at things that happen when there is a fault on either the line or on the load. We are not dealing with a source that is faulted. We're just looking at the effect of a faulted load or line. And this is the most common thing that you are going to go and find in your electrical career as well. It's very unlikely that BC Hydro has lost a phase. It's far more likely that your customer has lost a phase instead. So let's take a look at what we have over here. First of all, we're going to take a look at what happens when we end up with an open line off of our circuit over here. And because we're dealing with a delta type of system, we don't have a grounded system inside of here. We are going to go and have some movement of where we're going to go and see voltages across components. And they give us a couple of diagrams inside of the binder over here showing us this and this and this. But once again, this is something that is best seen through use of a physical piece of equipment over here. Over here, let's just pick that up there again. Over here, what we see is we have got a delta type of circuit. We've got our three different lines, which are represented by these three nails that are placed inside of the wood over here. And then we have got our voltages, which are being stretched across due to the fact that we've got these lines. Remember how we talked about the fact that anytime that we have got voltages, we can talk about that as if it were tensions. And what we see inside of this setup over here is that we're going to go and lose our line C. So we're going to go and lose this pin, which is representative of the line. When we do that, what we see happen is we see that this phase over here is going to be unaffected, the one that's represented with the yellow. These other two phases are going to go and snap directly across from point to point, but they're each only going to go and see half of whatever I had for my voltage. Because we know that from here to here was a value of 208 volts, therefore, half of this is going to be 104, half of this is going to go and be 104. And it's just because we've lost this line, which before was stretching it out and across to there, that we now have these sort of an issue. Once again, we'll just pull that out over there to the corner. We'll put the nail through the plastic grommet and drop that one in. This is what we normally have. We have a three-phase system that is tensioned across the load. We have voltage across the load, but as soon as we lose any one of our lines, we are going to go and have one phase that's going to be unaffected, and then the other phases that connect to the affected line, those are going to go and single phase across here as well. They're going to be shortened up, and so they're going to go and see half of my line-to-line voltage. If this is 208, they're going to be seeing 104. If this was 600, these two would each be seeing 300 that would be placed across them. Let's go and do some calculations now based on us having that together. All right. Just going to move this stuff so everything quits falling all over on my desk. Okay, so over here, we see that we have got a three-phase AC supply. We have got three loads that are connected in delta across this, and then we are going to go and lose one of our lines. And as soon as we go and lose that line, we go into single phasing at this point. Effectively, what we have is we have got two of these phases that are now going to be seen as being in series going across from line to line. We saw how they just snapped across those lines as soon as we lost that anchor point that we had before on our C line. So let's go and talk about what those values themselves are actually going to go and become. Let's start with this one over here. What we had is we have a 208 volt three-phase supply. We'll highlight that over there. It's something that's given to us. We have got a resistance furnace that is composed of 10 ohm resistances. Each one of these is going to be 10 ohm resistance connected in delta across here. And when we go and lose this line over here, we saw what happened, that these two are basically going to go and snap across line to line like that. So let's go and do a bunch of calculations. First of all, before we do that calculation, let's just take a look at what this delta furnace would be normally putting out for power. Okay, we're going to start with a good piece of equipment, then we're going to go and figure out what we have going down from there. Taking a look at this, because it's a delta system, I know that my E line is equal to my E phase, which if my E line is 208 volts, that means my E phase is also going to be 208 volts. So we can drop that onto any one of these resistances. 208 volts, we've got a value of 10 ohms, and 208 volts. What we can do is we can figure out what we have got for phase current. And to do that, we're just going to go and take our E divided by R. Volts divided by resistance, 208 divided by 10, tells me that I'm going to go and have an I phase of 20.8 amps. So inside of here, under normal operation, I'm going to go and have 20.8 amps. And I'm going to go and have 20.8 amps through each one of these individual loads. The problem is that these phase currents are going to go and come together at these nodes, and then they're going to go and enter and exit along these lines. I know my arrows are going backwards to what the drawing is, but this is AC, so it's always alternating back and forth in between there. What we need to do is we need to go and calculate our line value of current, and our line value of current for this is going to be found through our delta I line is equal to I phase times root 3. So we're going to go and calculate that. We're going to go and take my I phase 20.8 and we're going to multiply that by root 3. All right, let's go to this one. So we have got my I phase, which is 20.8 multiplied by root 3. Which gets me to a value of line current of 36 amps. Okay, let's go to 36 amps then. We end up with a line current of 36 amps. I'm just going to erase all of these calculations and say 36 amps as my line. Based off of that line current, I can now go and figure out what I would have for my total power. Because these are all resistive, my VA is the same as my watts. So we're just going to go 208 multiplied by 36 amps, 208 volts, so it's 36 amps times root 3. This is my E line times I line times root 3, calculation that we've done so many times already in this course. And we're just going to go and punch that into our calculator. All right. 208 times 36 times root 3 equals 12,969. That's going to be our total amount of power that this system would normally be putting out. So I'm just going to write that one down as being my original 12,969 watts. Normal power that we would have out of this system. Let's go and find out now what happens when we go into this single phasing. So as soon as we single phase, we lose that line over there, which means that this 20.83 that we had, all of that is going to go and change. We're going to go and delete a bunch of this, but we're going to keep a couple of things. First of all, what I want to note is that this phase over here, completely unaffected. Before it was connected across from line 1 to line 2, it is still connected across from line 1 to line 2. It is still going to go and have its regular value of voltage over it and its regular value of current through it. So we can go and calculate that one. Its current is going to go and be 20.83, and we know that because it's 208 volts across it, divided by 10 ohms, which is going to go and get us to 20.8 amps. So we got 20.8 amps that is going to be through here, 20.8 amps. And if we want, we can figure out the wattage of this single element alone. Let's just quickly go and do that. We're going to go and take 20.8, our current, and we're going to multiply that by our value of voltage, which is going to be 208. 20.8 amps multiplied by 208 volts equals a value of 4,326. So this element has got 4,326 watts. You should recognize as well that this value is 1/3 of what I would have off of a normal system, because it's a balanced three-phase system. Each of my individual watts, or each of my individual elements, is going to be providing 1/3 of the total power out of this thing. The next thing that we're going to do is we're going to go and examine these two. Well, these two now no longer have that connection, which means that they are snapping across in series over top from line to line. If you refer to this picture over here, it's the exact same thing as what we would have here. It's 208 volts, but now we would have a 10 ohm and a 10 ohm in series. We can add two series resistances together to go and equal 20 ohms. And if we've got 20 ohms over top of 208 volts, we are then going to be able to go and find a new value of current. 20.8 or 20 ohms and 208 will do 208 volts divided by 20 ohms. That's going to be my E over top of my I, or sorry, over top of my R, not my I, which is going to go and give me my I. 28.8 divided by 20 is going to go and give us 10.4 amps that we are going to go and have through this. So I'm going to go and get a total of 10.4 amps. That's going to go all the way through from my B line to my A line. I see that I've got a voltage of 208 volts that is pressed across them, so I can figure out my total wattage of both of these together by using the total current through both of them and the total voltage across. This is 208 multiplied by 10.4. Let's just take that into our calculator over here. 208 multiplied by 10.4, which gets us to a value of 2,163. Let me just take a look over here. We'll just write that one down. 2,163 watts. That is the total amount of watts that I'm going to go and have from the combination of these two placed in series. If you wanted, you could have also gone and figured out each of them as an individual resistance with the current through it. You could have done like an I squared R, found out the individual watts for each of these, which would have been half of this 2163, and then added them all together. But I just bypassed that step because it's much easier for us to work around it. Okay, so we're going to go and take that value of wattage that we calculated for these two, 2,163 watts. We're going to go and add it to our watts from the good working element over there. So plus 4326 plus 4326 equals a value of 6,489. What we see for the total watts of this entire circuit, 6,489 watts total. If you take a look at that value that we just calculated when we were single phasing, and if you go and compare that to what would happen when I have got a complete system, you should see the relationship right away. It's 50% that we are going to go and have across here, basically. 6,489 divided by 12,969. We'll just do that. 6,489 divided by 12,969 equals 50%, 0.050036. A little bit of rounding error, but we can see that effectively once we go into the single phasing, we are going to go and drop down to a 50% power output. There's also going to be some weird values of voltage that we are going to go and measure across these ones as we are looking at them. If we were to go and take our meter and place them across the A phase or across the B phase or across the C phase, we'll just quickly do that here a second. We're going to go and see differing values of voltage. What we should have, if this whole thing was operating correctly, is we should have had 208 volts across any of the elements. It wouldn't matter which one that I would be looking at. But right now, because we've got that open line, this one here is going to go and see 208. This one here is going to go and see 104. And this one over here is going to go and see 104 volts across it as well. So my A, my B, my C all have voltage that is going to be measured across them, but it's going to be smaller amounts that we are going to go and have off of the two that are attached to the line. And it makes it easy for you to troubleshoot because you say, hey, which do these two have in common? Well, we see that they both have in common the fact that we have got a line C over there. That line C, therefore, must be the one that is faulted out. Okay, 50% when we have got a open line when we are dealing with our delta type of systems. Let's go and take a look at now what happens when we have got a delta type of system where it is the load that burns out. We're not looking at the line anymore. We are going to go and look just strictly at the load. First thing before we do anything is we are going to go and calculate, first of all, let's just go and see what would happen if we had a good load. Okay, I'm just going to repair this over here. Yeah, we'll stick a box around that. Looks good. And we're going to go and say, what would be my total amount of power that this thing would normally put out? I'm working off of example number 3, 10 ohm resistances that we see. Delta supply, 208 volt supply over here. We did that calculation for this one over here. We had 10 ohm resistances, 208 volt. And we found out that we had a total, when we went through that calculation, and you can go back in the video if you need to go and take a look at that again, our total for the good one was going to be 12,969 watts was going to be good. Okay? Because we already know what that value is, we can now go and compare it with what happens when we actually go and lose a load. And when we lose a load, we are once again going to go and have something that is going to go and happen. Before, when we lost a line, we saw that this happened, where we had one phase that was unaffected, the other one, when we lost that line like that, as soon as we lost it, we saw that two phases got a short voltage that were placed across it. One phase still had the original line value of voltage that was across it, and we overall dropped all of our power down to 50%. What we're going to do now is we are going to go and open up one of the loads themselves. So over here, I have got my good delta system, the way that we calculated it before, and now what we're going to do is we're just going to go and cut across this one. And as soon as we cut across over there, what do we see happens to that one? Well, we see we have no longer any complete path for current flow going through here. I'm sorry, my camera is just autofocusing like crazy these days. But there's no complete path through here. But we see that this one and this one over here, both are completely unaffected. They're still attached to the same lines. They've still got the same value of voltage placed across either one of these. This is the only one that's gone. I can infer, I mean, I don't even have to do the math, but I can just look at this and say, well, if that phase still has got the same voltage over top of it, the same resistance stretched across it, therefore it's going to have the same watts. It's going to be dissipating, and this guy should be doing the exact same thing. Looking at that, if this is the same watts, this is the same watts, I should have 2/3 of my power that's going to be left inside of the system. Let's jump over to that calculation and just go through the mathematical proof on that. All right, working with this one over here, we see that we have got 208 volts. We see that we've got 10 ohm resistances that we are going to go and have. What we're going to do is we're just going to figure out our power for a single one of these. So far in this course, we've been using all of our easy cheesy values. You know, we've been using watts as being calculated by my volts times my amps, but let's just go and change it up a little bit here. We're going to go and use a different formula. Do you guys remember this one here? Watts is equal to E squared over top of R. I'm going to use that one. I love that formula. We're going to use it a lot more throughout this course because it bypasses a bunch of small steps. Particularly, this bypasses me having to go and calculate current. Current is what changes in a circuit. Resistance is physical. It's based on what the circuit itself is made out of. We don't see loads of changes to resistance most times. Voltage is going to be determined by the source. It hardly ever changes as well unless we have a faulty source, but that's pretty rare. So usually it's going to be our current that's changing. Since that's kind of a changeable value, I prefer not to go and work with it. Let's figure out our watts for this element, and we can do that using our value of resistance and our value of voltage that's being placed across it. My line voltage for a delta, E line, is equal to my E phase. Therefore, 208 volts line is equal to a 208 volts phase that I'm going to go and have. Let's go and put them into this formula. 208 squared divided by 10 is going to go and give me my watts for this element over here. We're going to go and bracket it because brackets are free on your calculator. Don't just cheese out on me. If you drop brackets and you put them in wrong, you can sometimes screw your calculations. I'm going to go 208 squared, bracket, lock that off as being the top of mine, divided by 10 equals 4,326.4. This is the same value as what we had before in the previous calculation because it's the same heaters that we're using. We saw that when we were looking at this one before, we saw that this heating element right over here, well, not that, but this heating element right over here that was unaffected, we had that same 4,326. We're now going to go and see that same value, 4,326. That is going to be placed across this one. 4,326. We're also going to go and see the exact same value because we've got the same resistance and the same value of voltage, 4,326 watts. That's going to be placed across that one. So my A phase over here is gone, but these other two are still developing full power. And what I can do, watts never lie, I can just add my watts together. 4,326 plus 4,326 is going to go and give me my total amount of watts left. I'm just going to go and multiply this value by 2. Gets me to 8,652. 8,652 watts. And that's what I'm getting right now when I've got an open load off of this thing. Is that a percentage? You bet it's a percentage. 8,652, what I'm getting underneath this open load on my delta over top of my original, we can calculate that. Divide it by 12969 equals 0.667. Once again, this should be something that you recognize as being a 2/3%. In other words, if I get an open load, this element over here, completely unaffected, just carries on making power. This one, completely unaffected, carries on making power. 2 out of 3 elements are carrying on. Therefore, we have got a total of 2/3 power when we have got that open delta load that we have over there. Okay. Last thing that I'm going to go and point out over here is going to be my values of voltage that I'm going to go and have. If I have got an open load, my values of voltage are going to go and be 208, 208, and 208. Remember, we can have voltage without current. If it's open, there's just voltage across that gap. So if I've got an open load, I have got voltage that is across that load element. If I have got an open line, let me just go and erase these over here. What we had in the previous one, I've got voltage across all of my different elements, but the voltages are not correct on 2 of them. These ones over here are 104. They should be 208. That's how, when I'm measuring out my loads over here, I can instantly tell, is it an open line or an open load? If I've got a delta load, and I have got 2 small voltages and 1 larger voltage, that's got to be an open line. If I have got a delta system that's not putting out full heat, you know, that's what the customer is going to be telling you, but I've got proper voltage over top of every single element, that means that I have got a dead element that's going to be somewhere inside of the mix. Okay, that's that for your open delta calculations.